When you run a deep learning application on a single local machine, you eventually hit a physical wall. The server must handle the interface, the logic, and the raw computational crunching simultaneously. To solve this, we separate the system into a three-tier architecture, dividing the application into presentation for the interface, logic for processing, and data for storage. The challenge lies in translating these three tiers into isolated, scalable units that can support the high compute demands of deep learning. The presentation layer requires continuous uptime to serve the website files, regardless of what is happening in the backend. The logic layer needs the ability to expand its compute capacity on demand to process machine learning tasks. And the database layer has a strict requirement for permanent, uncorrupted storage. This diagram on the left shows a local setup where all three layers share the same physical constraints. On the right is a cloud environment, a grid of potential capacity. To bridge the gap between these two worlds, we use Kubernetes as the orchestration engine to manage how these tiers interact. We are going to build this deployment from the ground up, mapping the infrastructure, the containers, and the networking. This separation is required because storage tied directly to a compute instance is lost the moment that instance restarts. Decoupling the two is the only way to ensure the application's data survives its own execution. Every cloud environment relies on a foundation of physical hardware and virtual machines. This is known as the infrastructure layer. We start with the control node, the management hub for administrative commands. It handles kubectl commands that dictate cluster state. Next, we deploy the worker node. Running an Ubuntu virtual machine, this is where the application lives. While the worker node provides raw CPU and RAM, the environment is volatile. Virtual machines don't guarantee that hard drive data will persist if the system reboots. To solve this, we use a Kubernetes mechanism called a persistent volume claim to secure permanent disk space. This claim is mapped to a physical folder on the worker node's hard drive at /mount/test-SQL. This directory acts as permanent storage for the application's data, separate from the temporary compute memory. By isolating the persistent volume claim from the general compute area, we ensure the database survives even if the virtual machines cycle power. With the foundation set, we move to the container layer. Kubernetes organizes application code into pods, the smallest units of execution in the cluster. We assign each architectural tier to its own dedicated pod. This ensures they do not compete for the same computational resources. The presentation tier is housed in the front-end pod. This pod uses Nginx to serve HTML and JavaScript files directly to the browser. The logic tier is contained within the back-end pod. This container runs Python and FastAPI to process logic and prepare machine learning tasks. The data tier is managed by the database pod. It runs MySQL, the system designed to store and manage the application's entries. The database pod is physically linked to the storage vault beneath it, ensuring all data writes are directed to the persistent volume. Because these tiers are isolated, a heavy machine learning task in the Python backend can consume maximum CPU without freezing the Nginx frontend. These isolated pods now need a way to communicate with each other and the outside world. We use node ports to open specific, secure access points through the worker node's perimeter. Port 30080 is the first entry point, exposing the Nginx frontend to the user's web browser. Port 3008 is the second entry point, allowing the FastAPI backend to receive incoming data. Inside the Python code, a coarse security handshake validates that the website on port 30080 is allowed to talk to the API on port 3000. For internal traffic, the database pod remains hidden. It is never exposed to a public node port. Instead, the backend locates the database through internal service discovery. This relies on a DNS lookup using the designated name MySQL service. Kubernetes handles this address book automatically, abstracting the internal IP routing away from the developer. This dual network topology creates a controlled path for public interaction while shielding the core database within the cluster's internal network. With the architecture complete, we can trace the lifecycle of a single piece of data through the system. A user on a laptop sends a JSON packet containing the name John to the cluster. The packet enters the perimeter through port 3008 and is received by the FastAPI backend. FastAPI validates the data and converts the request into a SQL insert command. The command travels across the MySQL service internal pipeline and enters the database pod. MySQL writes the data into the physical.ibd files stored inside the persistent volume claim. To see the resilience of this setup, imagine a catastrophic failure where the database container crashes and disappears. In milliseconds, the Kubernetes orchestration engine detects the crash and instantly provisions a brand new replacement pod to take its place. Because the storage was decoupled from the pod, the new container simply reattaches to the physical volume, where the John entry is still safely stored. By architecturally decoupling ephemeral compute pods from persistent storage volumes, the system becomes a production-ready engine capable of scaling intensive deep learning workloads.